Okay, this is question 6 from paper 3, 2019. This question is about radioactivity. Gold has 1 stable isotope and 36 radioactive isotopes. The first thing we're asked to do is define the term isotope. So, the answer that we're looking for here is an atom with the same number of protons but different number of neutrons. Okay, and that's an atom of the same element. Okay. That's the answer that we're looking for there. All right. Part A2. Explain what happens in the nucleus when a beta particle is emitted. So this is only 2 points, so we're just looking for a brief definition here. Verbally describe what happens during beta decay. Okay. So during beta decay, we have a transformation of a proton in the nucleus into a neutron. And at the same time, we have an emission of an electron that was created in the nucleus. Okay, so we can write that very simply. A proton is transformed into a neutron, and an electron is emitted from the nucleus. Okay, very simply. So 2 things. Your 2 points. Number 1, a proton is transformed into a neutron. That's 1 point. And an electron is emitted from the nucleus. That's your 2nd point. Okay. Part B. The figure shows a rolling mill which produces thin sheets of aluminum. The thickness of the aluminum is monitored using a beta emitter, gold 198, a Geiger-Müller tube, and a counter as shown below. Okay, so just so we're clear what's going on here, these 2 rollers are being used to press the aluminum to thin it out, and then we have a gold 198 source right here, so that is going to be giving off radiation, and that radiation is going to be detected underneath here by the Geiger-Müller tube. As you know, aluminum is a material that is used as a shield from a specific type of radiation. Do you know which one? Okay, if you said beta, then you are correct. Okay, so yes, beta particles cannot pass through aluminum. Okay, now if the aluminum is very, very thin, then some may be able to get through. So this is why it's a great detector to use in a situation like this. So if the Geiger-Müller tube, the count is high, it means that the aluminum foil is too thin, and so the rollers need to be adjusted. They're pressing it too much. Okay, so that's what the counter is used for. When the count is low, then that means the aluminum foil has the right thickness, and the beta particles that are being released from this gold 198 source, they're being blocked, okay, because the aluminum is thick enough. All right, so I basically just explained everything that we're probably going to be asked in the next question, but let's go ahead and zoom in on what we're actually asked. All right, so the first thing we're asked is what happens to the count rate when the thickness of the foil decreases. Okay, so that's what I just was talking about just now. If the thickness decreases, so it means it's getting thinner, then we expect that the count rate will increase. Okay, count rate will increase. And that's because there are more beta particles passing through. Even though aluminum is used as a shield from beta particles or from beta radiation, it has to be at least 4 millimeters thick. Okay, if it's thinner than that, then it's not as effective. All right, the next part says, why would gold 173, which is an alpha emitter, not be suitable for monitoring the thickness of the aluminum sheets? Okay, so alpha particles have an even shorter range than beta particles, and they will be completely blocked by aluminum. So that would not be a good indicator because the count would always read 0. So that would not be useful at all. So alpha particles would not be able to pass through aluminum at any thickness. Okay. Now, if you wanted to use an alpha emitter as an indicator for the thickness of maybe paper, which at below a certain thickness, some alpha particles may be able to get through, then that would be a similar setup like this. Okay, instead you'd have where the aluminum foil is, you would have paper. Okay, so the next part is the graph. So I want you to pause the video right now and go and plot your graph, and then come back and we'll talk. All right, so let's look at the graph. The graph you plotted should look like this. It should not be a straight line, it should be a curve. Okay, so before you start to answer any questions, make sure that your graph has a title. Okay, you have your title. Make sure your graph has both axes labeled. Okay, here, down here with the quantity name and the unit there. Make sure you have your scale and make sure that all your divisions are equal. Okay. All right. Let's look at the questions over on the next page. So we're asked, first of all, of course, to plot a graph of count rate against time. Time is always on the x-axis for these types of graphs. So make sure that that's correct. X is the horizontal and Y is the vertical. All right, we're told to determine from the graph the half-life of gold. So recall that the half-life is the time taken for the original sample or the current amount of that sample to decay by exactly half its amount. Count rate was 6 originally. Divide that by 2. That takes us down to 3. So what we want to know is what is the time or how much time has passed. Remember, when you see half-life, that is a value of time. Okay? How much time has passed when it has decayed from 6 to 3? So you're going to go from 3, touch the graph, and come down. And you're going to determine that value, read that off. Okay, so you should get about 2.7 days. If you get 2.6 or 2.8, you're good, you're in the ballpark, okay? The next question, the time when the count rate is 4.7 times 10 to the 5 seconds, okay? So how are we going to determine that? Okay, so remember that all of your values are to the order of 10 to the 5. So you just need to go to 4.75 on your graph. Okay, so let's find that. It's a little light on my graph, so I'm going to draw it again for you. 4.75 is going to be about here. Let's use a different color. So that's 4.5. Halfway between that is 4.75. Go over to the graph, and then we're going to come down. You can kind of see my line right there, but that's the point we want to read. And you should get about 0.85 days. Okay, plus or minus. All right, so half-life, remember, that is the time taken to decay by half the original value. Half-life is time, remember, time taken to decay by half. All right, the next thing we need to determine is what is the count rate at 3.8 days. So this time we're going from the x-axis and getting the corresponding y value. So we're going to go to 3.8 on our graph. So that's my blue line that I'm going to draw. So 3.8, that's right here. I'm going to go up, touch the graph, and go over. It's a little wobbly, but you should get 2.15, 2.15. And remember to put the order of magnitude, everything on that graph. If you look at your table of values that you had in the beginning, everything is times 10 to the 5. Okay, so that's the unit. So you can just put that back there when you're writing your answers. Okay, so that would be the count rate. And that's per second. So you put the correct unit back. All right, so this next question says, give 2 reasons for the use of gold-198 in nuclear medicine. Okay, not 2 other uses, 2 reasons why it's used in medicine. Okay, and usually when we talk about the appropriateness of a particular isotope in a particular context, it has to do with its half-life and its penetrating ability. So for gold-198, the reason why it is good for use in medicine is, number 1, it has a short half-life, only 2 days. Okay, so it's not going to stay in your body long and cause any permanent damage. So short half-life. The second reason is that it has a short range. So we're talking about its penetrating ability, how far it can go, how thick of a tissue can it get through, okay, or how far it can travel through the tissues in your body. The reason why you don't want to have something that has a very long range, gold-98 is used to treat cancers. So tumorous groups of cancerous cells called tumors are injected with gold-98. When the gold-98 decays, the tumor is destroyed, but because beta particles don't travel very far, it will only be able to decay in the area and in that contained space. So the tumor will be destroyed, but the healthy tissues around the tumor and maybe under the tumor will be safe because the beta particles don't go that far and they won't stay that long. So those are the 2 reasons: short half-life and short range. All right, last but not least, the last question. Okay, to clear up this area here so we can solve this. Yeah, maybe not all of that. Let's just get some space. Okay, all right, smaller. Okay, so this is going to be where I'm going to put the working for the last question. So we have a calculation to do. Gold 195 has a half-life of 186. Gold 195 has a half-life of 186 days. Don't confuse the two. Those are two different isotopes, two different mass numbers, two different amounts of neutrons. So the one with the short half-life that's used for medicine is gold 198. This is a different isotope of gold. So this is 195. It has a half-life of 186 days. You do not want to put that in your body. All right. A sample of gold 195 has a count rate of 8,000 counts per minute. So that's our starting point. 8,000 counts per minute. How long would it take the sample to fall or decay to 125 counts per minute? So first we need to know how many half-lives have passed. Each half-life corresponds to 186 days. A half-life passes every time the count decays to half its original amount. So we need to know how many times it does that before it gets to 125. So all we need to do is just keep dividing by 2 until we get to 125. So let's do that. So 8,000 divided by 2 is 4,000. That's one half-life. 4,000 divided by 2 takes us to 2,000. That's two half-lives. 2,000 divided by 2 takes us to 1,000. That's three half-lives have passed so far. 1,000 divided by 2 takes us to 500. That's four half-lives that have passed. 500 divided by 2 takes us to 250. That's five half-lives that have passed. And if we divide 250 by 2, we're going to get 125. And so a total of 6 half-lives have passed. And if one half-life is equal to 186 days, the total time taken for the count rate to fall to 125 is going to be equal to 6 times 186, which is 1,116 days. Okay, so 1116 days. All right, so that is your question. That's the end of the question. 1 point for doing this little bit here, finding out how many half-lives. Another point for doing this little calculation, and of course for stating your answer correctly. All right, that's it.